Alright, so today we're aiming to finish off our discussion of like semi-simple algebras and all that with a couple short chapters here. After that will be Ito's theorem, and then things are going to get crazy. But anyways, today's first topic here is the invariance theorem. So we're going to let G be a Lie algebra with a representation rho on a vector space M. Oh, okay, and this is going to be this kind of talk. For every class delta of simple representations of G, let M delta be the isotypical components of M of species delta. The subspace M naught of invariant elements of M is M delta naught, where delta naught denotes the class of the zero representation of G on a one-dimensional space. And comes with a lemma. We're going to take three representations, rho, sigma, and taf of G on vector spaces M, N, and P. Suppose we have a k-linear mapping from M and N to M dot N of M times N into P such that rho of X times M on N plus M with sigma of X on N is equal to taf of X times M dot N for all M in M, N in N, X in G. Now, the lemma goes as follows. Part A, if M naught is in set M0, the mapping of N, the map just given by left multiplication by MO, is a G module homomorphism. B if n is in n delta, then our MO of n is in P delta. If M is an algebra, and the images of X in G under rho are derivations of M, then MO is a subalgebra of M, and each M delta is a right and left MO module. And the proof, we have that taf of x on MO.n is MO on sigma x n for all MO in MO, n in n, x in G, thus A. With A implying B by a result from algebra, and C is a special case of B where n equals P equals M and sigma equals taf equals rho. Now we have another lemma immediately afterwards. Suppose further, so we have all of the above, that our maps sigma and taf are semi-simple, and so n is the direct sum of the n delta, similarly with P. For all n in n, let n sharp, n natural, and that's not a sharp, I should know this, be its component in n naught, similar for P in P. I'm going to let MO be in MO. Then for all n in n, MO on n natural is MO on n natural. By linearity, we consider only the case n is in n delta. If delta is not delta 0, then n natural is 0, and MO dot n is in P delta. So that MO dot N is just natural. Natural is equals O is just MO on N natural. If delta equals delta 0, N natural equals N, and MO on N is in PO. So MO on N natural is MO on N is MO on N natural. Alright, so after that we have another theorem here. Let G be a Lie algebra. V a semi-simple G module of finite dimension over K with symmetric algebra S of V, symmetric algebra of V, and XS, each XS be extending XV such that X to XS is a representation of G on S, of course. And there's two conditions to this. A, the algebra, which we're going to call S0, of invariants on S, is generated, invariance of S, not on, generated by finite elements. And condition B, for every class delta of finite representations, simple representations of G. They are finite, but that's a different part. Simple representation of G of finite dimension over K. Let S delta be the isotypical component of species delta. Then the isotypical component of species delta is a finitely generated S0 module. Our proof. Let S prime and S be the ideals. The ideal of elements of S with a no constant term. Let I be the ideal generated by the intersection of S0 and S bar, and let the elements of Si from 1 to P be a finite system of generators of I. And we can assume freely that the Si belong to the intersection of S0 and S bar and are homogeneous. XS, preserved degree, and so each S delta is a graded submodule. We're going to let S1 be the subalgebra of S. It's going to be the one generated by 1 and the Si. Then S1 is an S0. We show S1 is S0. And we do this by showing each homogeneous S in S0 is in S1 by induction on N, which is the degree of S. Once again, with degree 0 is trivial. So we're going to suppose N is greater than 0 with the condition having been shown for N smaller than the one we're working with. As our S is in I, S is the sum of Si prime, where Si prime are assumed to be homogeneous elements of S with degree of Si prime equal to the degree of S minus the degree of Si is less than N. By our previous lemma, S is S natural is the sum of Si prime multiplied naturalized is the sum of Si prime natural. And we see that these Si prime natural are elements of S0 which are homogeneous and of degree less than n. And so by the induction hypothesis, are in S1. Thus S is in S1, which means S is equal to S1, which is what we wanted for A. Now for B. So we're now going to consider a simple representation of G of class delta on a finite dimensional M. We're going to let L be the k-linear maps from M to S. Then for all S in S and F in L, we let SF be in L defined by, so this is a MS linear map where S of F on some element M in M, of course, by the definition of this element on the left, is S on F of M. Thus L is now an S module as M is finite dimensional over K, then we have that L is a finitely generated S module, and hence is Noetherian, keeping in mind that S itself is definitionally Noetherian. We also have that L has a canonical G module structure for integer n of at least 0. We're going to let Sn be the homogeneous elements of S of degree n. So that Lk of M or S to the n is semi-simple. And hence the G module L is semi-simple. Then for S in S, F in L, X in G, M in M, the L map of X on S times F M is XS of SF of m minus SF of xm of m, which is definitionally S times f of m minus f of xmm, which is xss of f of m plus s of xsfm minus this s of f xmm on the right, which gives us xss of f of m plus s of xlf of m. Hence, xl of sf is equal to xs of s f plus s of xlf. Alright, so a little more to go here, just a little more. I believe we get, sorry, give 1 second to look through everything here. Now we see the subset L0 of invariant elements of L is the set of homomorphisms of the G module M into the G module S. Hence, if phi denotes the canonical homomorphisms of the K-tensor of M on L onto S, phi of M tensor K of L0 on the left is going to give S delta. As phi is an S module homomorphism, we need to show that L0 is a finitely generated S0 module. We're going to let J be the S submodule of L generated by L0. Since L is a Noetherian, S module, there exists a finite sequence Fi from 1 to Q of elements of L0 generating J. let L1 be the S0 module generated by this Fi. Keep in mind that J is an S module, this is an S0 module. Then we have that L1 is an L0. If F is an L0, then we can write F as the sum of Si Fi with Si in S for all I. So, and hence F is its own image in S naught, F natural, which is the sum of Si Fi natural which is the sum of Si natural Fi inside L1, hence L0 is L1, so L0 is a finitely generated S0 module. And we are finally done this theorem and this chapter. We have another chapter here to go through. Thankfully it's a short one. Last chapter of this section. So you know what it's going to be. Change of base field. As you do. Let K1 be a commutative extension of K. For Lie algebra, G over K let's reword this. A Lie algebra G over K is semi-simple if and only if that GK1 is semi-simple. As the killing form beta 1 of the extension of G is derived from the killing form beta of G by extending the base field so beta 1, that's not even a letter I drew. Beta 1 is non-degenerate if and only if beta is. So, if G extended to K1 is simple, we have from the above that G is semi-simple at the very least. And we also have that it cannot be the product of non-zero ideals so G is in fact simple. However, there is simple G with its extension G to K1 being not simple. But it will always be semi-simple. So, now we're going to let R be the radical of G. Then the extension of R by K1 is the radical of GK1 if S is the nilpotent radical of G, the nilpotent radical of G extended to K1 is the bracket of G K1 with R of K1, which is the extension of the bracket to K1, which is equal to the extension of the nilpotent radical. So G is reductive if and only if G extended to K1 is. Let G be a Lie algebra with a subalgebra H. So recall that a representation of H is semi-simple if and only if the extension of the representation is. Hence, H is reductive in G if and only if the extension of H is reductive in the extension of G. Now we're going to let K naught be a subfield of K such that the index of K naught in K is finite. Let G be a Lie algebra with G naught the Lie algebra derived by restricting base field to k naught. Every commutative ideal of G is a commutative ideal of G naught and if A naught is a commutative ideal of G naught, the smallest vector subspace of over K of G containing A naught is a commutative ideal of G. Hence, G is semi-simple if and only if G naught is. With okay. If G naught is simple, then G has to be. Now, if G is simple, G naught is. How do we know this? Let A naught be a simple component of G naught. For all lambda in the multiplicative group of K, lambda A naught is an ideal of G naught, and the bracket of A naught with lambda A naught is lambda of A naught and A naught is lambda A naught, which is non-zero. Hence, lambda A naught is contained within A naught. Therefore, lambda A naught is A naught. Just use an equal sign because this we are in math. Since the K naught dimension of lambda A naught is the K naught dimension of A naught, the vector subspace of G generated by A naught is a non-zero ideal of G and hence is G. And that is the proof of our assertion, and that is the end of our chapter. Up next is Ado's theorem, and then after that, I think we might go into root systems, I guess. After this, I gotta check over, make sure everything's good. Make sure, like, there's nothing about any of these types of matrices that are covered in the other books, not in this one. And then we will be going into, like, I think we'll be going into, like, root systems, Cartan matrices, that sort of thing, hopefully.